So that I know from Hooke's law that as I apply a force to a material, it will stretch. Now, it's not always visible. If I take a slinky or a rubber band, yes, I can pull on it and it will stretch. But there are other things like a steel beam or this pencil. I can pull on the pencil and it will become longer, but you don't necessarily notice that. And some materials stretch better than others. So Hooke's law is still in application here. If I take a steel rod and I pull on it, it will stretch some amount delta L. And so let's just sort of see where that goes. I apply a force, and how much it stretches is proportional to it. If I take that equation and divide by the cross-sectional area, A sub naught, times the initial length, in essence, by the volume, on both sides, it should still be equal. That's what the math people tell me. And then I will go ahead and multiply both sides by L sub 0. And I'm not going to cancel L sub 0 out because what I'm ultimately looking for is a proportional relationship. All of this right here is a constant. K is the spring constant, A is the cross-sectional area of the object, and L sub 0 is the initial length of it. And so what I end up with is for a particular bar is that the force divided by the cross-sectional area is directly proportional to how much it stretches divided by the initial length up to a certain point. At some point that falls apart, and we will get to that in just a moment. We define stress to be the force divided by the initial cross-sectional area, also known as longitudinal stress, where longitudinal direction is along the direction that the force is applied, as opposed to the transverse direction, or lateral direction, which is perpendicular to that. It's called a normal stress if the force is parallel to the area vector, and the area vector is perpendicular to the surface. And then there's longitudinal strain or linear strain, or what I generally refer to as strain. I believe that the other ones are the ones that require additional qualifiers. So if I just say stress or strain, these are the ones to which I am referring. And then, so based upon that, my stress is proportional to my strain up to a certain point, what's known as within the elastic limit. If I look at units, the units of stress are the units of force over the units of area, which is a Newton per square meter, which is a Pascal. The units of strain would be the units of length over the units of length, so it's unitless. You could also do meters per meters if you wanted, or if you wanted to unnecessarily do meters per centimeter, then you have an extra factor of 100 in there, but usually not done. And then you can also put it in percent form since it's just a number, multiply times 100%, and so you can end up with a percent. So if we plotted stress versus strain, then it should be a straight line up to a certain point within the elastic limit as mentioned earlier. Since it's directly proportional, then sigma is equal to some constant times the strain, and that constant is known as Young's modulus. It's also sometimes referred to as the modulus of elasticity. So if it's Young's modulus, I'm using the letter Y for Young's modulus. Some textbooks will use E for elasticity. And so I will tend to use Y because the textbook I'm using right now for this topic is using the letter Y, but again, some will use the letter E. The units of this would be the same, since that's unitless and that has units of Pascal, that must have units of Pascal. Now, if I continue with it, at some point it is going to start to curve here, that you're going to enter what is known into plastic deformation. So officially, the yield strength is the point at which the plastic deformation would be 0.2%. In other words, that delta L over L is 0.002. So it's once you're past that, officially you've hit the yield strength. This point right here where it stops to be proportional is sometimes referred to as the proportionality limit, and those are usually very close to each other. Now, what happens right here, some diagrams will have it come up like this and then sort of do something like that before it moves over around like that. The nature of what's happening there depends upon the material and how simplified do I want to make the drawing. The point up here, the maximum amount of stress it can take compared to the original area is known as the ultimate tensile strength. At this point, if you've ever taken a plastic ring and pulled on it, then you will hit something known as necking. And so as a demonstration here, I've got this bit of plastic, and as I pull on it, notice it's getting thinner and thinner and thinner. So we get this point where it suddenly thins down quite a bit. So it's basically the original width before, and then it gets down to this narrowing part. This is known as necking. That happens at this point. Now, there are times in which it is at an advantage to be able to actually do that. If I take a rod that I know can stretch farther, I can purposefully stretch it farther to put it at this point. Now, when I let go, it's going to come down like that. I'm going to have some permanent strain added to it, but it takes a lot longer before it will deform. So when they were building the St. Louis Arch, they did something like this, is they put the rods into the concrete and then they stretched them so that they would not deform. Now, granted, when you get to this point right here, it's going to break really easily if you exceed that stress. However, the advantage is you're not going to end up with twisted metal. So if I have the arch that kind of looks like that, if I did not strain harden it, then there's a more likelihood that the thing might twist if you exceed the yield strength. But now it requires more to get to the ultimate strength, and so that would be an advantage to that. But wherever you stop, so if I stopped, so I'm taking a metal and I'm pulling on it, if I stopped here, this would be sort of the permanent strain, and this would now be the new elastic region. This type of stress and strain where we compare things to the original amount, so this is the length over the initial length, and this is the force over the initial cross-sectional area. This is known as engineering stress and engineering strain. In a moment, we're going to get into another way of looking at it. And there we are. So if you don't want to base it on the original dimensions, but base it upon the dimension at that moment. So if I'm doing the force over the cross-sectional area at that moment the force is applied, then you end up with what is known as true stress. And if I look at the strain based upon how much does it change relative to the current length, it's known as true strain. And so if I plotted stress for strain, we get this red, what I've drawn in red here, very similar to what I had before, but true stress and true strain plotting tends to keep going up. And so that ultimate tensile strength would be here. And this is the point of breaking. So there is a different way of looking at it. My recollection from when I was doing engineering is we looked at stress and strain, the engineering stress and strain. Maybe there's a reason to call it engineering, as opposed to the true, but it's just another way of looking at it just in case you run across it. So let's take a look at the various stresses and strains. So there's tensile stress if the force is pulling on it. So tensile, think tension, versus compression stress as you push in. Shearing stress, force over area. So I have a block that I now push across the surface like this, and it will distort. It will go from something like this to something like that. That would be shearing stress, or sometimes called tangential stress. And then there's volume stress, as if I have pulling on it from all sides. That arrow should be down, considering all the rest are also pointing out. In terms of strain, there's longitudinal strain or linear strain. This is what we've dealt with. There's volume strain, so change in volume over the initial volume. Shear strain, to go along with shear stress, is that as it distorts, it's this angle right here. And then transverse strain is as I pull on an object this way, so this now becomes the longitudinal direction. What happens here is the transverse or lateral strain, and it deals with the change in width over the initial width. And we will definitely explore that in some other videos. And then lastly, when dealing with stress and strain, there is sometimes two useful variables that are used, alpha and beta. So alpha is the longitudinal strain per unit stress. In essence, when you're talking in the longitudinal direction, strain over stress, which is in essence just 1 over Young's modulus. And then there's the transverse strain per unit stress. And we will definitely use these as we explore a little bit more. Alpha times sigma, so this is just, since that's longitudinal strain over unit stress, multiply times the stress, you get the longitudinal strain, which is just the stuff that we talked about earlier. So these will come back.